This is Dr. Carroll, and this is a video about one of my favorite topics, hash tables. So let's go through a couple exercises to get to know them better. So for example, describe how hash tables work, including the underlying data structure and what is a hash function. Hash tables store items in an array. That's the underlying data structure for a hash table, is an array. So then how does hashing work? A hash function hashes, is the term we say, a key to determine the location to start to look in the hash table for the key. Doesn't mean it's going to be there, but that's where we start looking. Let's go on to the next question. What would the hash function look like if a string is used as the key? Well, first what we'd want to do is convert that string to a number and then use modular arithmetic. There's a couple different ways to do it, but that brings us to the next point of what are the requirements for a good hash function. So first off, and this is why I love hashing so much, is a hash function has to be fast and easy, those go along together, to be able to compute. And so there's some assumptions we're making about hash functions, or at least some expectations that they're going to be fast, and that's what makes them so amazing. Also, a good hash function is going to place items evenly throughout the hash table. If they're bunched up in an area, if we have clustering, that's going to cause problems. Third, it needs to involve the entire search key, and this is going back to the second question. If it's a string, we'd want to use the entire search key to build up the value that we're going to use for the hash function. Lastly, if we're doing modular arithmetic, which is very common, we want to use a base that is prime. That's going to help us avoid some patterns and in terms of looking at locations and things like that. So where would we use a hash table then? There's lots of applications. Let me just name a few. For example, a compiler identifying keywords or looking for identifiers, password verification. We could use pattern matching in strings, including plagiarism detection. Determine if two arrays contain the same contents. So if you have an array with some elements, doesn't have to be sorted, an array with other elements, you want to say, hey, what's this? Are they the same? Are things in there? We could just put all of them in a hash table, go through the other one. If they're in that hash table, remove them, and then look to see if anything's left over. That'd be a lot more efficient than an n-squared algorithm, which would be a naive algorithm to look for each element in the other one. Histograms. I love histograms, and so including maybe word frequencies. Those have become popular in the last decade or so. And if there's lots of different dynamic languages, Perl, Python, JavaScript, Lua, Ruby, and they use hash tables to implement their objects. So the keys here are the names and the members and the methods, and then the values then are the pointers for the corresponding member, for example the method. So that's pretty cool. Let's move on to another set of questions focused on handling collisions. Collisions are inevitably going to happen, and so we need to know how to be able to address them. Let's talk about several different strategies applying to a very small hash table so it'll fit on the screen really well. Just 7 entries. And so let's track what's in the array, the underlying array. If we're inserting the following values, 7, 11, 71, 42, 13, and 49. So the first question we need to ask is, what is the hash function? If it's not explicitly given, then it's going to be the value, that the key remainder the table size, or modulo the table size. That will very efficiently calculate it and keep it within the bounds of the array. Very efficient. It fits all the requirements. We're using all of the number. It's fast and efficient to calculate. It's using a prime because our table size is going to be a prime, and all of that. So let's get into it. So we start out with 7, remainder 7. Well, that's easy enough. That is 0. So we'd put it in the first position. Now 11, remainder 7 is 4. So we'd put it there. The next number is 71. Let's see, 70 would be 0, so 71 is going to be 1. No collisions yet. Now, spoke too soon. 42 mod 7, though, is 0. So what we're going to do is we're going to insert it at the beginning of the list of values that are at the same slot. So we could pictorially represent this as 42 is now in the first position and 7 is in the tail position at slot 0. If we insert 13, it could go to slot 6. If we insert 49, once again a collision, and we're going to insert it at location 0 again, inserting at the beginning of the list. And there we go with separate chaining, a very popular collision resolution scheme. Now let's move on to a whole new class of collision resolution schemes, and starting with linear probing. And again, the question is, what is our hash function? And so what we're going to do here is we're going to take our original hash function as h of x, and we're going to add in f of I, the probing sequence, and then take that result and take the remainder of the table size of that. So we're going to add to it. And so f of I for linear probing is just simply I. And so as I increases, then we'll increase what we're looking for. This has the effect of start at one place and then just increment, go through the slots incrementally after that. Very simple. So again, fast and easy to calculate. And so let's go through this. So again, inserting 7 is going to, so if there's no collisions, it's going to result in the same sequence. So 7, 11, 71 are all going to be in the same spot. Now when we go to insert 42, we have a collision. And so then we increase I. So now I is 1. And then we have a collision again, this time with 71. And so now we increase I again, and so we have h of x is 0 and f of 2 is 2, so then we put 42 in slot 2 because we originally looked at the slot at 0. There's a collision there, and so linear probing doesn't allow for more than one value to be at a slot, and so then it goes to the next one and goes to the next one. This is the same algorithm, by the way, that we use to insert it, we're going to need to use to find it as well. If we insert 13, we're fine, we put it at the end. 49, though, is going to have a collision at 0 again, and then with our second try at index 1, there's a collision, index 2, there's a collision. We can finally put it at index 3. With quadratic probing, we're going to change the probing sequence so that we avoid primary clustering and we jump further and further. We take larger and larger steps to jump. Now, these hash tables are extremely small. They're just video size, not real world size. So it's going to be a little artificial what's going on here with the sizing. But if you can imagine a large hash table and then taking steps instead of just incrementally, but we're going to jump further and further and further away to avoid some primary clustering. So when we go to insert 7, there's no problem. We can insert that once again at slot 0. Oh, let me back up. First, we need to establish what is the hash function. So it's the same as before, but with a different probing sequence. This probing sequence, we're going to take the iterative value squared and then mod that by the table size. Okay, and so there we go. And so 7, there is no collision. It's going to map to 0 again. And then real quick, an important attribute of f of I, the probing sequence, is that when I is 0, that it equals 0, which we have here. When we go to insert 11, same thing, no problem, no collision. 71, same thing. But now when we insert 40, when we go to insert 42, we have a collision. And so we say, okay, well, what is the hash function for 42? And so we could calculate it. When I is 0, we're going to get 0 plus 0, mod the table size 0. And now there's a collision there, so then we could go to I squared. So I is 1. We're going to get 1 mod 7. There's a collision there as well. We're going to increment I, and I is going to be 2, so 2 squared is 4. And then 4, there's a collision there. It's almost like someone designed this intentionally for that. Weird. And then we're going to increment it even more. 0 plus 9 mod 7. And then we're going to look at that. And finally, that equals 2. And so we're good. And so we can insert 42 at 2. Now the next one, 13, there's no collision, so we put it at slot 6. And then we move on to the last number, 49. So the hash function here is, we're going to apply it when I is 0, then we have 0 plus 0, there's a collision. When I is 1, then we're going to have 1 squared, and so there's a collision there as well. We increment I again, and we get I is squared, so 0 plus 4. We're following the same sequence as before. That seems problematic. And we've already seen this one before. Yep, this is what we did before, so we need to keep going. I is 3, so now I is 4. And so we get 16 mod 7, that equals 2. I is 5, slot 4 is taken. I is 6, slot 1 is taken. And we go on and on and on and on until I equals 500, and that still doesn't work. And so the numbers just keep going up and up, and then we have this problem. So what's going on here? Well, it's extremely small table, but we should have rehashed before we got to here. And so that's a big takeaway for this one. Let's look at the next collision resolution scheme, double hashing. First question answer again is, what is the hash function? We're going to follow the same convention with looking at a probing sequence, but the probing sequence is a little different here. We're going to use I times another hash function, h sub 2. What is h sub 2? We're going to use r minus the result of x remainder r. And so you might be asking, what is r? R is the prime number just smaller than the table size. So that has some advantages. We're still relying on prime numbers. And so that will be our probing sequence. Once again, we are going to start with trying to put 7 in. F of I is still going to be 0, and so we're not going to have a collision. We can put 7 in. We can put 11 in as well, and 71. And now when we get to our next number, 42, we get a collision. And so we apply our hash function with a little bit more attention to it. So h sub 2 of 42, well, what is r? R is going to be 5. So then we're going to take 5 minus the result of 42 mod 5, and so that's 3. And so notice how h sub 2 depends on the key that we're trying to hash. And in this case, for 42, we're going to multiply I by 3 so that we're resulting in a different probing sequence for 42 compared to another value. So h of 42 is our original hash function plus our probing sequence. Starting out with, and notice when I is 0, we still get 0 for the probing sequence. So we have 0 plus our probing sequence, and we still get 0. And that leads to our collision. When I is 1, then probing sequence result is 3. We add that to our original one, and we get 3, which is an opening, so we can place it there. Now we go on to the next one. 13, there's not a collision, and so we can quickly and easily put it at index 6. Now when we have 49 here, this really highlights the value of double hashing. We have a collision, so we need to employ our collision resolution scheme, and so we need to calculate h sub 2. H sub 2 of 49, notice, is 1. And so that's where the power of this comes in, is we had a collision with 42 and its multiplier on its probing sequence was 3. But when we have a key of 49, the multiplier on its probing sequence is 1. And so then we can calculate, well, what is the hash function for 49? Well, it's 0 plus 0, 0. We've already seen that one. We've already talked about that one. Now when I is 1, we get 1 times 1. And that spot is also taken up. Now 2 times 1, well, index 2 is available, and so we can put it there. And notice we have a different probing sequence than we did for 42. And if we went to look for 49, we would recalculate h sub 2 and then be able to follow that probing sequence to be able to find it. Let's go on to the next question. We have these 4 collision resolution schemes that we've just employed. Now what is the load factor alpha for each of them? Well, so let's start with the first one. The load factor alpha is calculated as the number of items divided by the hash table size. Well, we had 6 items that we were cramming into a hash table size of 7, and so that was for the first one. But notice, the calculation is actually independent of the collision resolution scheme, so the load factor alpha is 6/7 for all of them. Well, all of them that could get the items in that didn't have a fatal flaw. Let's now talk about rehashing. We saw that we needed to rehash, but we hadn't, so let's talk more about it. So what is rehashing, and what are the major steps for that? So what it is we're going to increase the hash table size. The way we do that is by creating a new hash table with a table size that is the next prime number larger than twice the previous table size. So that, and then each item has to be rehashed into the new hash table. So this can be computationally intense, but it is necessary when we get too full, if we underestimated the size needed for our hash table. Why do we do it? Because we want to avoid collisions so that we minimize the number of iterations needed for a probing sequence, so we can very quickly either insert or retrieve. So then the question is, when do we rehash? Well, when the collision rate is too high. Well, what is too high? For separate chaining, when the load factor alpha is larger than 1. For linear probing, when it's about larger than a half. Quadratic probing, when it's about greater than 2/3. Now let's talk about hash efficiency in relations to different collision resolution schemes. So the advantages and disadvantage. So starting with separate chaining, the advantage is it's simple. There's less rehashing, at least compared to open addressing methods, because our threshold is set higher. The worst case efficiency though for inserting and searching is order n. We may have to rehash. So we should use if we need to allow for deleting keys and or more insertions than the table size. So under those two circumstances, we should use separate chaining. Let's move on to linear probing. So it has better cache performance because we're analyzing the neighboring locations than say quadratic or double hashing, but it's subject to clustering. It also has a worst case efficiency of order n because we might need to rehash. Moving on to quadratic probing, the performance is about in the middle, except we're not subject to primary clustering like we saw with linear probing, just secondary clustering. Its worst case efficiency is still order n. On to the last one. Double hashing has poor cache performance, but virtually no clustering. So that's a big win. Worst case efficiency is still order n. So if we're not planning on deleting keys and the number of elements that we're going to insert is less than the table size, then this is a good one to go with. To conclude this video, just a miscellaneous topic here, we need to be careful about the constants in hash functions. This will help us avoid issues like collisions and not cycling through all the slots for open addressing and etc. I hope you enjoyed this video. Thank you for watching.